Since the beginning of this series, we've presented mechanics from one particular kinematic perspective. The assumption was that we observe some kind of motion, like an explosion, or the pinching of a water droplet, or the fall of an object, or the orbit of a planet. With these examples, we represented motion by plotting a length versus a time. That length could be a size or a distance, and the time could be an indefinite duration, or a recurring period. Size or distance, duration or period, the types of length or times, matter less than their dimensions. The observables, the variables, are kinematic. They depend on time and space. We've seen that these kinematic power laws can be remarkably understood by invoking mechanical quantities, or mass-carrying quantities, involving the dimension of mass, beyond those of time and space. Motion emerges from the interactions of these quantities. We've seen that the interplay of a pair of mechanical quantities, Q1 and Q2, produces a single kinematic power law, D equals K times T to the power alpha, where the kinematic prefactor K and the dimension as exponent alpha are obtained from the underlying mechanical quantities, following this general equation. X1 and Y1 and X2 and Y2 are the space and time dimensions of the quantities Q1 and Q2. As soon as we know the relative dimensions of the two mechanical quantities Q1 and Q2, we know the scaling connecting kinematics and mechanics. So far, with this formula, we've assumed that D and T were two distinct but correlative variables, two columns of the same spreadsheet if you like. This particular dataset was used by G.I. Taylor to track the trajectory of Trinity, the first nuclear explosion. In this case, the dynamics are due to the interplay of the energy E of the bomb and the density ρ of the ambient medium. In this context, the size and time are indeed the coupled variables, and the energy and density are constant parameters. Knowing the values of just two parameters allow to predict a potentially infinite series of sizes d for each time t, or to recover the times if the sizes are known. Actually, from an initial variable, here time, not only the size d can be predicted, but any kinematic metric built from the size and time. Basically, you can fill as many columns as you like by combining the first two columns in different ways. For instance, if the exponent x of the size is equal to 1 and that of time is equal to -1, then the third column is the average speed of the front, which can be computed for any time point. Whereas the size grows over time, the speed actually decreases. The validity of Taylor scaling can be checked by measuring the size over time, or the front speed over time, or the front speed at various distances from ground zero. We introduced this in the last episode of the explosion series. The dynamics emerging from a particular pair of mechanical quantities can be represented from different kinematic perspectives. Not all dynamics can easily be understood as the evolution of a length over time, and it is sometimes much more practical to use different pairs of kinematic variables. To each pair of kinematic variables correspond a different perspective on the dynamics. Translating from one perspective to another is what we'll learn to do in this episode. Let's start again with Trinity. In this situation, the pictures of the explosion provide a direct way to measure the radius of the blast, d, over time t. We've seen that from this perspective, the interplay of energy and density leads to the now famous 2/5 power law. Now we will keep the time variable for the horizontal axis, but for the vertical axis we will represent the average front speed we just computed from the data. We get a different power law. The algebra is pretty straightforward. The average front speed decreases like a power of time with an exponent of -3/5. This scaling, just like the 2/5 power law for the radius evolution, is the direct consequence of considering the interplay of energy and density, once the variables are set, here v for the speed, on the y-axis, and t for time, on the x-axis. Note that what we call the front speed admits a few different definitions. For instance, one may be interested in representing the instantaneous speed of the front, the local derivative of the radius curve. Since the radius grows proportionally to time to the power 2/5, this instantaneous speed is just proportional to the average speed, and the scaling remains the same, but it is just slightly shifted down. We discussed these subtleties in more detail in the last episode of the explosion series. We will ignore them in this episode and keep in mind that these kinds of numerical factors are absorbed by the approximate equality sign. The average speed contains the degree of precision we'll be satisfied with for now. In this example, the kinematics are still represented as a time series. The x-axis has not changed, and the changes we made to go from the radius evolution to the speed evolution were quite limited. So it is not too hard to see in this -3/5 power law the same mechanical signature that in the original 2/5 scaling. We will now consider the case where one of the variables is the speed and the other is the distance. One important application of this perspective is in aerodynamics, where one is interested in representing so-called velocity profiles. We started with an explosion as seen from the perspective of its size versus time, while the power law has an exponent 2/5. Then we just saw the explosion from the perspective of its front speed versus time, while the exponent is -3/5. Now to get to the front speed at various distances from ground zero, we can use the radius over time to express the time from the radius, and then substitute this expression in the speed versus time equation to get the speed versus distance or size. Here the exponent is -3/2. Same event, same physics, but different perspective. This is the type of data one would get by recording the speed of the front as it passes by at different distances away from ground zero. This kind of representation where a speed is plotted against a distance is what is sometimes called a velocity profile in aerodynamics. To illustrate this, we can come back to a situation we've seen on several occasions already, the simple shear flow. Recalling episode 3 on simple times, we know that the deformation time in this flow is a simple time, given by the ratio of viscosity and stress. The viscosity eta is that of the fluid and the stress sigma is imposed at the boundary. We saw that one way to understand this deformation time was as the inverse of the gradient of velocity. So the ratio of viscosity and stress is related to the ratio of distance and speed, which are correlated variables, since the speed is varying with the distance away from the boundaries. We can rearrange the equation in such a way that it becomes clear that what we're dealing with here is the viscosity stress regime as seen from the perspective of a speed versus a distance, that is, as a velocity profile. In this particular setup, d is the distance from the immobile boundary. The speed is proportional to the distance, so the profile is a straight line in linear scale or in log scale, while the slope of the line is just 1. Measurements of this kind of flow profile have been conducted on countless occasions. The data points you see here are far from the best illustration of this regime, but they are good enough for now. The deviation for the furthest points is due to the fact that this shear flow was obtained on curved boundaries, as it occurs between two concentric cylinders. We'll come back to this when we learn how to deal with transitions between adjacent regimes with different exponents. In this example, the profile corresponds to a very viscous fluid, with a viscosity more than 60,000 times that of water. 61 pascal/second, that is kilogram meter minus 1 second minus 1, and a boundary stress of 183 pascals, that is kilogram meter minus 1 second minus 2. We know that behind this scaling is none other than Newton's simple time. But when this duo of stress and viscosity is expressed as a speed over a distance, one speaks of the Quet profile, or Quet flow, after Maurice Quet. This simple shear flow is what naturally comes out of the interplay of stress and viscosity. Speed varies linearly with distance. Another very useful flow is the pipe flow. Here the profile is not linear, but parabolic. Why? In this situation, the viscosity of the fluid is still relevant, but the flow is not driven by a stress at the boundary, but by a difference in pressure along the conduit. The pressure upstream, sigma 1, is greater than the pressure downstream, sigma 2. The impelling factor of these dynamics is the gradient of pressure, that is the pressure drop, sigma 1 minus sigma 2, over the distance, capital D, for this drop to occur. A pressure or stress divided by a distance is a force density, psi. So in such pipe flow, the two important mechanical quantities are the fluid viscosity eta and the force density psi built from the pressure gradient. If seen from the perspective of a speed versus a distance, this pair indeed produces a parabolic profile, signature of the quadratic relationship between speed and distance. In this situation, d is the distance away from the center line. Which side doesn't matter. The speed requires a little change in reference frame. V is the speed in the co-moving frame, that is, the maximum speed in the center minus the speed in the lap frame, in black. Rotating by 90 degrees, we get a speed growing quadratically. So in log scale, we get a slope of 2. When the interplay of viscosity and force density is represented from this perspective, one speaks of the Huygens-Poiseuille flow, after Gottlieb Huygens and Jean-Léonard-Marie Poiseuille. And this scaling has been around for quite some time now. The data on this plot comes from a recent study by Grégoire Lemoult, for water in a conduit with a rectangular cross-section. The shape of the cross-section has an impact on the dimensionless prefactor delta. In the simplest case, for a pipe with a circular cross-section, the prefactor is 1/4. Well, that was the velocity profile obtained by pairing force density and viscosity. And we've also seen stress and viscosity, and energy and density. 3 examples of velocity profiles obtained from dimensional analysis. We could go on trying different pairs from the table, but it is time to move to a different kinematic perspective, that of dispersion relations. This viewpoint on kinematics is rooted in the study of waves, where one is interested in relating the frequency of waves and their wave number, that is the inverse of their wavelength. So this perspective connects the inverse of a time to the inverse of a length. A water strider generates waves as it moves on the surface of water. In this case, the waves are rather short. But if you drop a rock in water, waves of a different kind are generated. When dealing with waves, the perspective of a size growing with time is not really practical. For waves, the size, or height, or amplitude, is oscillating up and down with time. How can our champion power laws be of any use to describe a situation like this? Well, it's all a question of choosing the right perspective. On a plot like this, the time we should be focusing on is the period of oscillation. And for each snapshot of the wave pattern, we want to be recording the different wavelengths between adjacent crests. Obviously, this wavelength is variable, and what we seek to understand is how the wavelength depends on the period of oscillation, or vice versa. Then one is of course free to represent the frequency rather than the period. It's a question of taste. Similarly, we can use the inverse of the wavelength, which is called the wave number. The symbol for the frequency is usually f or omega, and the symbol for the wave number is q or k. We'll use omega and k. Again, what matters is their dimensions. The frequency is the inverse of a time, and the wave number is the inverse of a length. Such kind of representation is called a dispersion relation. Alright, now that we're done with these definitions, we can return to what's going on the surface of water. What we are seeing here is a mixture of 2 kinds of waves, which are based on 2 regimes we've already encountered. The surface tension and density regime, and the force density and density regime. We've already seen what these 2 pairs produce when seen from the perspective of a size versus a time. We encountered the first regime in the context of pinching water droplets, and we saw the second regime at play behind dam break flows or avalanches. If we now switch to the perspective of a dispersion relation, we get 2 new power laws, which are again direct consequences of dimensional analysis once the impelling and impeding factors are known, and once the perspective is chosen. Let's focus on the first. This kind of dispersion relation corresponds to capillary ripples, small waves impelled by surface tension and impaired by the density of the fluid, here water. This regime was first studied theoretically by Lord Kelvin, a character we've already encountered in this series. and it is Rayleigh who first tested this regime experimentally, another Englishman we've met before. Here are more modern measurements. As expected, the frequency is proportional to the wave number to the power 3/2, and the coefficient of proportionality is given by the ratio of surface tension and density, sweeping under the rug the numerical factor of order 1, as usual. Alright, now, what about the second dispersion relation? This regime concerns larger waves, where the force density in the fluid is more important than surface tension. This force density psi is usually a weight density, ρg, a substitution we've seen a lot. Then the regime can be written from the acceleration of gravity g. In this context, one speaks of gravity waves. They are famously seen on the surface of oceans, seas, lakes, and other bodies of water, but also in the sky. This regime has been known for some time, and it was used as a matter of fact by Kelvin at the end of the 19th century. It's been measured on countless occasions, and we will return to it in a future episode, when we will know how to deal with the transition between different regimes. Because we may rightfully wonder about which criterion can be used to know if we are to expect capillary ripples or gravity waves. We've actually seen the missing link in episode 2, when we introduced the capillary length. If the wavelength is shorter than this threshold, we'll see capillary ripples, and gravity waves otherwise. But let's not get ahead of ourselves. We've seen two examples of dispersion relations, the one coming from surface tension and density, and the one coming from force density and density. Now you know the recipe. You can take any pair of mechanical quantities and build the associated dispersion relation. This perspective is particularly useful when clear oscillations can be identified, with measurable frequency and wavelength. But what if the data are completely chaotic, with respect to space and or time? What are we to do then? We can build a spectrum of the data. A great example of this class of approach is the so-called energy spectra used in turbulence studies. In this context, for each wave number of dimension L-1, one usually plots a rather peculiar kinematic quantity with dimension L² T-3. If you are at all familiar with the concept of turbulence in fluids, you must have seen this plot already. It is Kolmogorov's minus 5/3 spectrum of inertial turbulence. A quite frightening beast if you're not used to it. First put forth by Andrei Kolmogorov in 1941. What we're going to see is that this regime is just like the others we've encountered so far, once we better understand the perspective from which it is seen. This requires a little bit of translation effort, so let's try to outline the task we need to accomplish. The only thing we already know is the wave number, k. But we have to explain what this epsilon is, and how to construct the y-axis, that is how to measure the fancy looking E here. But first, let's say where these data points come from. These data were obtained in British Columbia, near Vancouver, in a place adequately named Discovery Passage. This passage is a narrow tidal channel where the sea flows in and out with the changing tides. Grant, Stewart, and Moillier studied the turbulence of the seawater in this strait by recording fluctuations of the velocity of the flow with a probe attached to the boat. How did they do that? This question is connected to the definition of the variable E, the so-called energy spectrum. This variable is usually understood by invoking its integral over all wave numbers, which is defined to be 1/2 of the variance of the flow speed around its mean. This right-hand side can be interpreted as the kinetic energy associated with the velocity fluctuations per unit mass, hence the term energy spectrum, although E is a kinematic quantity. The variable E measures the proportion of turbulent kinetic energy at various length scales in the flow. Anyway, the goal of this channel is to avoid expressions like this with integrals and so on, so we'll only remember the essential. The variable E is connected to the magnitude V of the velocity fluctuations for each wave number k. If V and k are known, E is known. We can illustrate this by coming back to our squiggly line. In this context, the amplitude is the flow speed, once the mean is subtracted. This curve contains a continuum of wavelengths, small and large. The spectral perspective investigates the amplitude of the fluctuations for each wavelength. Let's make some room to illustrate this. Now, take one particular wavelength, which we can call d, which is associated with one particular wave number, k. The speed fluctuations at this scale have an amplitude v of k. The speed depends on the scale, which depends on the wavelength, and so on the wave number. If we consider additional wavelengths, we want to know how their amplitudes change depending on their wavelength. In inertial turbulence, larger wavelengths have larger amplitudes. More precisely, the amplitude of the speed fluctuations is proportional to the cubic root of the wavelength, and so proportional to k to the power minus a third. Then, since we know how the kinematic quantity E is related to the wave number and to the speed amplitude V, we can circle back to Kolmogorov's minus 5/3 spectrum. We're learning how to juggle with these different perspectives on the same physics. To gain a deeper understanding of what these physics are, we know the recipe. We have to take a closer look at this mysterious prefactor epsilon. From the dimension of E and K, we can infer that this epsilon is a kinematic quantity, with dimension L squared t minus 3. The value of epsilon is constant for a given dataset, like this one. Fitting the data would give epsilon around 2.9 10 to the minus 8 meters squared per second cube. How can we interpret such strange kinematic quantity? It is not a speed, it is not an acceleration. It's one of these weird quantities like the prefactor of Taylor's regime. And just like for Taylor's regime of explosions, this prefactor can be written mechanically. But which mechanical quantities are involved? What can we put for Q1 and Q2? This turbulent spectrum is called inertial because it depends on the density rho of the fluid. The density is the impeding factor. The greater it is, the less intense the turbulent fluctuations. What is the impelling factor then? It is the power density, that is the power per unit volume driving its flow. The density and power density are 2 columns and 3 lines apart, such that the dimensions of their ratio are indeed L squared t minus 3. This is the only possible pair using the tabulated quantities here. So, Kolmogorov's spectrum is the regime built by pairing power density and mass density. It is a direct consequence of dimensional analysis once the perspective is set. And these data points obtained on Discovery Passage provided one of its first experimental validation. Note that the data points at large wave numbers deviate from the scaling. Large wave numbers correspond to small length scales, and this departure in the millimeter range is actually due to the growing effect of viscosity, an additional mechanical quantity beyond the initial pair. We'll come back to this another time once we've learned how to deal with more than 2 mechanical quantities. For now, let's sum up what we have already. We've seen the face of inertial turbulence from different perspectives. First, from the perspective of the energy spectrum, which is the most well-known angle on these dynamics. We've also seen how the amplitude of the velocity fluctuations depends on the wave number. These different vantage points offer complementary ways to understand turbulence. We could also write down the dispersion relation. It relates the frequencies and wave numbers of the velocity fluctuations. Instead of the wave number, we can use the wavelength or size d, and this angle can be used to understand the behavior of so-called coherent structures, like the vortices, whirls, or eddies, which can be visualized with a laser and some smoke in the air, or with microscopic flakes in water. And they can be seen on a grand scale in the atmosphere of Jupiter, where they are naturally contrasted due to the varying chemical compositions tied up to these eddies. These structures are the face of velocity fluctuations in turbulent flows. They can be seen quite clearly in computer simulations. Vortices form entangling filaments, which deform and stretch over time. The vortices themselves can rotate at different rates, omega, which is called the vorticity. This variable omega is also connected to the zones between the vortices. There, omega is the extension rate, when the vortices rotate both clockwise and counterclockwise, or the shear rate, where locally the vortices rotate in the same direction. Through shear, extension, or rotation, omega is connected to the strain rate. And so the last perspective in this list can be interpreted as relating the strain rate to the characteristic size of the strain region, whether it is a vortex filament, or a shear layer, or some more complicated creature. In the past 30 years, such emphasis on vortices and other coherent structures have provided a new angle on turbulence, complementary to the statistical style of the spectral perspectives. To conclude, we can mention one last perspective, a size d versus a time t, which is the initial approach of this series. Mass density and power density are 2 columns apart and 3 lines apart, so we can get a size growing like time to the power 3/2. We know that one way to think about the variable d is as the size of a strain region. We know that we can think of t as the period of velocity fluctuations at this length scale, but also as the inverse of the strain rate on the fluid region of size d. Yet another way to think about it is as following the evolution of a strain blob of varying size d. We do not know a priori if the blobs are getting bigger or smaller, pinching like droplets. Small blobs might grow while others deflate. But anyway, dimensional analysis gives us the power law relating size and time. Although tracking this process for a single blob entangled in a sea of countless others may be challenging, there is actually a way to estimate what we would get by translating the measured energy spectrum. For d, the translation formula is simple. d just scales with the inverse of the wave number. What about t? Well, we know the relationship between E, K, and V, and we can use d instead of k. We can then express the speed as the distance d divided by time t. So E can be expressed solely from d and t, so the time t can be computed once the energy spectrum is known. These two translation formulas give a way to convert the dataset from the perspective of an energy spectrum to a size growing with time. This curve gives the expected evolution of the size of a strain blob over time. Note, however, that the conversion formulas are approximate, and that numerical factors like 1/2, 2 pi's, and the like may shift the curve right, left, up, or down. But the scaling remains. These 4 perspectives on turbulence, and any other we might like to adopt, are formally equivalent, but they collectively contribute to a richer and finer appreciation of the interplay between power density and mass density, the mechanical pair behind inertial turbulence. What we see is a combination of what is and of the perspective we've taken. And as illustrated in the parable of the elephant and the blind man, greater insight is reached by comparing what is perceived from different perspectives. We've seen this in some detail for the case of turbulence, but the lesson is general. For any pair of mechanical quantities Q1 and Q2, we know since episode 5 that the size versus time scaling is obtained solely from the dimensions of Q1 and Q2, the exponent x1 and y1, and x2 and y2. If we now want to represent the evolution of a speed, dimensional analysis gives us the right scaling. If the situation calls for it, we can also derive the velocity profile, or the dispersion relation, or the energy spectrum. We've only seen this perspective in the case of inertial turbulence, but there are many other kinds of turbulence associated with different pairs of mechanical quantities. We hope to come back to this at some point. In the more immediate future, we will tend to keep the first perspective, that of a size evolving over time, because it is very visual, and we now know how to translate this viewpoint to others. We can go from one perspective to another, but are they really equivalent? Well, not exactly. In the next episode, we will see that for each pair of quantities on the table, there is actually a privilege perspective. When kinematics are represented from the right angle, motion comes to a standstill and variables become constant.